now going to introduce this concept of random variables. So random variables are typically what we're working with. In some sense, we already alluded to this in the previous lecture, but let's get down a little bit more on terms of what it means to be a random variable and how we define them, both in discrete and continuous contexts. So first we're going to start off with discrete variables because we've already been working on that realm. And let's think about a random variable, for instance, being the sum of a pair of dice. So we're going to start constructing probability spaces and start looking at a random variable like x and start computing probabilities on this random variable. So for instance here, probability of x being 2 means that you rolled 2 ones, and the probability of each dice being 1 is 1 over 6, so 1 over 6, so this is 1 over 36. If we get a value of 3, here are the possibilities. There are 2 possibilities for the dice rolls producing 3. There's 2 over 36. And you can just compute all of these down here. The most probable then is when you have x equals 7, which is there are 6 different ways that can be done for the 2 dice rolls to produce 7. So you have a 6 out of 36 chance. In some sense, it's the most probable outcome. But this random variable x can be anywhere between 2 and 12. Those are the outcomes, right? Your sample space. And what you're really trying to do is define this as a random variable. In other words, if we assume that everything is equally a fair dice rolls, then this is the distribution that you would get from these random variables that you're working with, and this random variable being the sum of two dice. Okay? And so we can start putting together our probability calculations and our space, which is the probability of the union of these random variables taking on a value from 2 to 12 is the same as the probability, since these are independent events, right, is essentially from 2 to 12, which are the outcomes of the probability of each one of those different events. And of course that's the entire sample space, and so this is a probability of 1. So x here is a discrete random variable that you might be working with. From a picture point of view, I'm showing you here sort of the distribution, the number of times this happens, that like I'm just showing you that number of ways it can happen. So for instance, I already said that if you have a value of 7, there's 6 different ways this could happen, where there's only one way you can get 2 1s, one way you can get 2 6s and a value of 12, and then this is the distribution. And then as you start asking the question, what's the probability of this random variable taking on x equals some integer like 10 or less, 5 or less, this is called the cumulative distribution that you would get from this here, which is essentially this integrated starting from here, this side to this side. And I'll talk about this cumulative distribution in a moment. So let's keep going though with discrete versus continuous events. Coin flips are also discrete events. And the coin toss can have, let's say, probability p for heads and tails is 1 minus p. So this would be an unfair coin. If p was 1/2, then of course this would be a fair coin. So we can state it as p and 1 minus p for the probabilities. And so if I start looking at some of the different events of random variables that I'm going to define now as n, for n equals 1, which is having heads, it's probability p, but n equals 2 being tails heads, it's 1 minus p times p, because that's the probability of the tails, probability of the heads. 2 tails and heads is 1 minus p, so that's the square p. Or if I have n minus 1, n tosses, and n minus 1 of them are tails, and then followed by heads, then that's the probability there for that. So again, just another example of a discrete random variable that we might work with. And so now we start getting into some of the concepts, for instance, of what are called cumulative distributions. What's the probability that this random variable takes on some value less than or equal to b? So this is what we call f of b. This is a cumulative distribution, and the cumulative distribution is non-decreasing. So every time you add more events, it only goes up in value. Okay? The maximum value this can take, so in other words, if b goes up to infinity, is 1. Okay? So you accumulate all possible distributions, and the maximum value is, what's the probability of that happening? It's essentially saying, what's the probability of something happening inside of your state space, and it's going to be 1, or sample space. However, here is the opposite direction. If you take b goes to negative infinity, nothing happened, then it's 0. You're not counting anything that would have happened there that would hit this sample space. So, in other words, this probability this cumulative distribution takes on a value from 0 to 1, and it's only going up in value as b increases. We can also compute the probability, because now there's this nice relationship, because essentially cumulative distribution is the integral of the probability. So if I want to look at the probability of a random variable between a and b, it is the cumulative distribution of f of b minus f of a. So the way we compute this is to integrate it, take the limits f of b minus f of a, and that's how you would get this. So let's keep working on this idea, and we're going to keep going in terms of thinking about probabilities and defining also what's called a probability mass function. Probability mass function here for a discrete variable, p of a, little p of a, is the probability of the random variable taking on the value of a. Okay? So at least for a discrete random variable, probability x it's 0 if it's not one of the points. X is not equal to x of n, but this is some value greater than 0 for x is equal to x of n, where these are n different discrete values that it could take on. In other words, in some sense, some events that would be taken on. So these are how you would describe discrete random variables themselves. And if I add up all the n events or n possibilities of outcomes, then that probability density function, so notice the integral of it, is equal to 1. And the distribution itself, up to some a, is just the sum of the distribution for all values of x of n less than a. Okay? So this is your function here, evaluated over all the space. This is up to a certain point. And you can see here, I said it was an integral, and at least in the discrete case, the integral is just a sum. Okay? What about the continuous case? Well, the continuous case, you just replace all of those summations by integration. So x being in a set B, you just integrate over all B for some probability density f of x. So the probability density actually becomes a really important way of quantifying that random variable. And in fact, we'll talk about some common probability density functions that are used throughout science and engineering broadly. And so there's not that many that we use commonly, and so, but here's how you would start computing the probability of some event in space B. There's some nice properties of this as well. The probability function of x happening in the entire domain, negative infinity to infinity, is you just integrate over the probability density from negative infinity to infinity. By the way, this is 1. So the probability density, when you integrate over it, always has probability 1. In other words, you've integrated over the sample space, any event's got to be in there with so it's going to be probability 1 that it's there, and so that's what this statement says. However, if you think about the probability of it between a and b, you just take the probability density and integrate over that interval a to b, and that's going to tell you the probability of it between a and b. The actual probability of it being at a specific point for a continuous variable is basically the integral from a to a. So this is like, integrals are these sums of from a to b of a set of sums, but now you're a to a, so you don't have any width to integrate under, and so that is 0 exactly. Okay? So the probability of a very specific value happening in a continuous variable goes to 0. And so we can fix that a little bit by defining here in our continuous variables, we say that the cumulative distribution is essentially the probability distribution from negative infinity to a. In other words, you integrate up to the value of a. That's over this thing. So this f of a tells you I'm integrating from negative infinity all the way up to the current value. That's what this does. And the way to make sense about a probability distribution at a specific value is not to say x is equal to a, but rather x is between a minus epsilon over 2 to a plus epsilon over 2. So in other words, there's a little wedge there you're integrating. And so now you have this wedge to integrate over. And now the wedge width is epsilon, and it's a sifting function. So it pulls out the value of f at a times the width of your rectangle that you're integrating against. So that's the idea of a probability distribution over a small window, and what's the probability of it taking on a value over that small window. So common distributions, I've already said that these distributions are often things we work with, both in the discrete case and in the continuous case. But one of the most common ones here, as far as discrete goes, is the Bernoulli distribution, which is related to an outcome which is a success or a failure. So, or a heads or a tail. A single event and an outcome. So for instance, you could have an outcome, P of 0, with probability 1 minus P, and the outcome P of 1, which is the second outcome of probability P. 1 minus P and P have to add up to 1, so now there's probability 1. And so this is a binomial. You either get this result or you get this result. That's it. So this is a very common distribution used to just quantify success or failure, because those are the two outcome possibilities for at least this distribution. This is unlike the binomial distribution, which is also commonly used, but this is essentially the success or failure of n trials. So you don't look at just a single outcome, you look at a bunch of trials and events, and you ask the question, what's the probability of sort of essentially the cumulative success and failures? And here they are. You're basically saying, if I have n trials, then I have the probability of P of the success and 1 minus P of the failure, and essentially P of j is this factorial n over j, which is here, P of j, 1 minus P to the n minus j. So that's how you would quantify, let's say, a binomial distribution, which is not just a success or failure or heads or tail of a single event, but rather I did 100 coin flips, what's the probability of some outcomes with 100 coin flips, 1,000 coin flips, things of this nature. And a binomial distribution is how you'd model those kind of event structures in the discrete space. Then we can get into a Poisson process, which is still a discrete variable. The probability density, P of n, is the probability of the random variable x taking on a value of n is given by here. There's some essentially exponential parameterized by lambda, e to the minus lambda, lambda n over n factorial. And so this lambda parameterizes essentially how this Poisson distribution is laid out in terms of what the values are on this thing. So that's one way to parameterize. And often Poisson distributions are used for processes where there's some kind of wait time, where that wait time is randomly assigned through something like this. A uniform distribution. A uniform distribution is given by here. Now we're into the continuous case. A uniform distribution is, for instance, a simple way to do it is 0 everywhere except for, it takes on the same value in some domain, let's say between alpha and beta. So it's a flat distribution, non-zero in a certain domain. The area under the curve here has to be 1. Okay? And then we can also integrate that to give us the cumulative distribution, which is given by here. So this uniform distribution, let's say if you have a uniform distribution between 0 and 1, when you pick values between 0 and 1, all of them are equally likely. Okay? Whereas that you have things like exponential distributions and normal distributions, which are quite different. So the exponential distribution, this is a generalization essentially of that Poisson process for continuous variables, is lambda e to the minus lambda x for x bigger than 0 and 0 elsewhere. Here is the cumulative distribution. And again, we often use these kind of distributions to model decay processes, for instance. And then, of course, the most famous of them is the normal or Gaussian distribution, which is a distribution given by a Gaussian variable, offset by some mu, divided by some sigma here, and the mu is known as the mean and sigma as the variance. In a lot of science and engineering applications, if you don't know much about some statistical process, we often assume that it's just Gaussian distributed. And so what you compute with the data is a mean and a variance, and you just say, I'm going to assume it's normally distributed. Some really nice properties about normal distributions that you can make use of in that case, but also if you don't know anything better, this is not a bad assumption to be making. Where you get into trouble and things like this is when you have what are called fat tail distributions. In other words, when rare events, which are typically the tails of the distribution, happen more often than they're in real life, then this will let on, and then you have to maybe change the distribution, like a student's t-test or some other distribution, to essentially allow for a higher than usual probability distribution on rare events. But in general, a lot of people would just start off with assuming a Gaussian distribution, seeing how well it works out, and only modifying it if it's really struggling to model whatever you might be doing in your application. Once you have these distributions in place, you can start computing really important quantities like expectation values. And what the expectation value is, it's given by here. It's essentially the moment of the probability density. You can think of the expectation often casually as the mean value that's going to come out of an event. So here's the definition of the expectation values both in the discrete case and the continuous case. And again, the moment gives you sort of, from the point of view of calculus, is like the center of mass of a distribution. So it's like essentially it's the mean value that would come out for, at least from a statistical point of view. You can also compute these moments, expectations, let's say, of functions of your random variable, so g of x. So here we go. So now you did take the expectation of the g of x, you just throw the g of x in there and take the moment with respect to that, or you integrate across it here in this calculation here. So these are ways to compute not only moments of the random variables, but expectations of functions of that random variable as well. Moments are actually given by here, where you take, let's say, the random variable at its nth power. If you do it to the first power, e to the x, that's usually the mean. If you do it to the second power, e to the x to the squared, that's usually going to relate to the variance. If you do e to the x cubed, it's called this related to the skewness. And e to the x to the fourth moment is related to what's called kurtosis. So these are different ways of characterizing statistical distributions, and so they're just, whatever the nth power is, that is the moment arm essentially that you have to integrate against in a discrete case, or integrate in a continuous case against this to the nth power. So these are just definitions of how you would compute moments, and you can also generalize this to computing moments of functions as well. And it leads to a really important concept called the variance of a random variable, which is the expectation of x minus expectation x minus expectation. So expectation x minus the expectation squared, which you can write out as something like here, which is the expectation of the second moment minus the first moment squared. So this is what's known as the variance, and it's often a really key way of parametrizing a statistical distribution. So in fact, when we typically think about a Gaussian distribution or a normal distribution, the only two moments that are non-zero are the mean and the variance. Skewness, kurtosis are all zero, so we don't ever worry about parametrizing those when we have a normal distribution. And they're not that hard to calculate, so this is one of the reasons people really like working with normal distributions, is because they only have two parameters that completely parameterize that distribution, the mean and the variance, and here's how you would compute that variance. We can take this concept to multi-dimensions, so we can think about something like a cumulative distribution, the probability of x less than or equal to a, y less than or equal to b. So this is two variables, x and y. You can make x, y, z, as many variables as you want, and the idea is you just essentially generalize this concept here, and you have a distribution in the x direction, which is essentially, if you want to call this f of x, and what's the distribution looks like in the x direction, you look at essentially integrating out or looking at all y values, so y is less than or equal to infinity, or if you do it in the y direction, you essentially look at x being all values of x, which is essentially doing an integral in these different directions and integrating out the x or integrating out the y directions. And here's how you would do this. If you have a probability distribution for a and b in some space, then you just integrate over that space the probability density. And so, and if you, again, back to this concept, if you want to look at the probability of x being an a, you just integrate out all the y values, and that's from negative infinity to infinity, and you end up with now the distribution in the x direction over the a that you're looking at in this here. Okay, so it's like it's just multivariable calculus where you integrate out x or y, or you're looking at a joint area between the two of some a and some b, which would be the x and y directions. And again, you can generalize this to as many dimensions as you want. It's not just 2, it can be 3, 4, 5. Okay? So you can also compute expectations in the same way we did before. The expectation of some function is you just do the sum of that function over the domain that you're integrating against, or the expectation here, again, negative infinity, infinity, just take the function g of x of this against the density function itself, and that's how you do it in the continuous case and the discrete case. And this really brings us to some important concepts as well of independence. Specifically, are these two variables, random variables, x and y, independent? And the definition of independence is that you could say, if I have a probability distribution for x less than a and y less than b, that this is equivalent to the product of x less than a, probability density function of x less than a, times the probability function of y less than b. So if you have this, that means these two directions are independent. Or more specifically, the density function can just be written as a product in x and y. So when I do those integrals against x and xy, I can just do them separately because they have no dependence on each other. Okay? This also allows us to compute the expectation as a product, which makes it much easier if you do have statistical independence between these two. However, there are many variables that are actually not statistically independent. In fact, they are dependent, and so one way to get after that, how dependent are they, how coupled or how strongly linked are they are, is to compute what's called covariance. The covariance is sort of the leading way or standard way of computing essentially the relationship between two variables and how statistically dependent they are. So the way that's done, the covariance, is just, here's the definition of it. It's sort of it looks a lot like the definition of the variance, except for now you're taking the expectation of x minus e of x, y minus e of y, which you can write out it here, and you can compute this and compute essentially the covariance between two random variables. If you find that the covariance is 0, it means that the two variables are in fact independent. In other words, they have no relationship to each other. But when you get a non-zero covariance, in fact, if the covariance is 1, they're the same variable. Covariance is 0, they're completely different variables, independent variables. And so oftentimes in data, these covariance values take on values between 0 and 1. The closer to 1 you are, the more statistically dependent these two variables are. The closer to 0 you are, the more statistically independent you are. So, this idea of statistical independence, covariance, multidimensional probability distributions, this is all really important for us to start establishing early on, because many of the methods in the future that we will use in data analysis start to use these concepts to build models, and so understanding what these integrals are. Remember, all these probabilities are, it's just integrating things, right? So it's not like it's anything too sophisticated mathematically, it's just really doing integrals. But understanding the interpretation of what that means in terms of a probability distribution is really important. So that's the idea of random variables. We're going to work quite a bit with them, and it also sets up the entire structure for starting to understand how to use data and data analysis methods in practice.